on the device side alone, which is the where the interpretation of the signal data was done. That is at the low level or at the edge. We can look at the whole architecture later on if we are interested in it. But at this particular moment in time, if we look at the low level side of things, we have so many different options that we can get sense data or initiate some form of control. Okay, so we have the sensing and then we have the control that can actually happen. And the options that we have things like using a microcontroller. Let me just write this for micro and a microcontroller. Of course, this will be written as micro. I'm just using a shorthand. Or you can use things like programmable logic devices or FPGAs and other things as we go along. And we can talk about some of these into details as we go. Or we can use some application-specific integrated circuits. So there are different ways that we can implement the hardware, or we can get the hardware implementations. Of course, we've all heard of processors. And yes, we may have come across FPGAs, we may have come across ASICs, we may have come across microcontrollers. We just want to touch on them again to see where we've come from and also how we can actually make use of some of these, specifically with FPGAs. So if we take a microcontroller, you know, in here you have a processor, which in general interacts with memory for the fetch and execute cycle. So basically you write your code, or whatever is being sensed here will sit on a form of memory, and that form, whatever the lines of codes are, will be fetched from that memory by the processor and then executed by the processor. So the processor, you normally just fetch and execute information from memory. That's all the processor is doing: fetch, execute, fetch, execute. Now we can have this synchronized to some form of clock. So you can have a clock signal that is synchronizing some things, and of course you can divide the clock signal or you can multiply the clock signal, so you have things like timers in there. And we can have things like watchdog timers and other form of timers and all those sort of things. And this particular chip, for example, is sensing data from the outside world through its input and output pins, and again it's initiating control through its input and output pins. And of course there's power and then and ground going on in there. So we have some input and output logic taking care of that. So we have the I/O logic taking care of the power fetch and other things, right? If we put all of these on a single chip where we have the processor, memory, a bit of timers and other things, we get something called microcontroller. So we have our processor, microcontroller taken care of. Now you know that you notice that the microcontroller has a processor. The processor has its own instruction set, and the instruction set is just basically a bunch of instructions such as load, let's say load a register, or add, maybe let's say R2, R1, or multiply and accumulate MLA. So these set of instructions are dictated by the manufacturers, and we have to sort of follow the instructions, right, in order to communicate with this particular processor. I mean, someone has designed this architecture for us, and someone has of course fabricated it. A company has done that for us. But with an FPGA, basically we have the flexibility of creating our own chip, right? So it's programmable. You can create your own programmable chip. So we can write or implement something on the FPGA to create our own processor, or to create an existing processor, as long as we follow the right instructions, or we design it accurately. according to the way that manufacturers have laid out their data sheets, and also as long as the FPGA is large enough to accommodate the processor. We can implement some form of memory, we can implement some form of timers. So these individual chips or components, we can actually implement all of them using FPGAs. And of course, I love FPGAs because they are very powerful in the fact that we don't have to draw the circuitry for the chip, send it to a foundry, and then it will be implemented and come back to us later. No, we have the flexibility of basically programming the chip and implementing the chip in the lab and then reprogramming it again. So we'll be focusing on this for this next couple of days. And of course, there is the option of application specific integrated circuit. So the application specific integrated circuit is just a circuit that's specifically designed for a particular task. So in this particular case, if let's say we have a light sensor, we have, let's say, a smart meter, right? And we say we don't want to use a microcontroller. So historically, we've got, if you see memory, you have a memory, the memory we talked about that the processor was interacting with. So we have a processor, we've got memory, and there's the fetch and execute cycle going on. And let me see, processor memory. And even the memory, we had some bit of memory where, of course, if you leave a device, a program device somewhere in the field or maybe in the forest somewhere to do some sensing for you, you want your code to be written down on something that is somewhat permanent, right? So we have volatile memory and then we have non-volatile memory. And the volatile memory, for example, is RAM, which simply means that if you turn off your computer and turn it back on, you will lose the information that is available on the memory itself, right? So basically we say, okay, well, how do we implement some form of memory that we will keep the code so we don't lose it whenever we switch the power off, right? So we have some of the non-volatile memory. We would have heard of ROM, read-only memory. Simply means that, of course, this memory upon manufacturing will be programmed, and once the fuse are set, basically we can't do anything to it again. It becomes read-only, which means that we can only read from it. We can't write to it again. Then there is an option for us to program a read-only memory. So sorry, it's become a PROM, not that. So let me get rid of this one. So later we say, let's make it possible. So it's read-only, all right, but we make it possible in such a way that we can at least program it once, right? So let's look at a programmable read-only memory, how the architecture looks like. So one is programmable, and two, once you program it, it becomes read-only. That's what PROM is. So we have our gates where we have X and then maybe Y as our inputs. And because these are 2 bits, 2 to the power 2 is what? Equals 4. So we have 4 possible combinations, right? And then Z is our output. So we have 0, 1, 0, 1. And then we have 0, 0, 1, 1. And if we pick an AND gate, it simply means that both inputs need to be 1 for the output to be 1, which means both inputs need to be true for the output to be true. So wherever we have 0, 0, the output, let me write out here, the output will be 0, and when we have 0, 1, the output will be 0 throughout until both inputs are true. That's when we have 1. So the AND gate is represented by that symbol. So we have 2 inputs in our case, Y and then X coming in. Y and X have to be 1 for the output Z to be 1. Same way we can have our OR gate. So we have our X and Y, the same 4 possible outputs, Z out for OR gate. And the OR gate symbol is that. So we just wait on there with it. So we have 0, 0, 0 1 0 1, too far bottom, it won't work. And then we have 0 0 1 1. At least we get the idea. So for 0 0 will be 0 0 1, all means that at least one of them have to be true for it to be true. So 0 1 will be 1, 1 0 will be 1, and 1 1 will be 1. That's for OR gate. As long as any of the input is 1, the output will be 1. So we have X and then we have Y. This can be 0, that can be 1, and the output will be 1. So that's just a quick so then that takes us to one that has both the programmable and arrays, and then you have a fixed array OR gate. Before we had the programmable OR gate, and then we have the fixed array, the fixed NAND gates. So these ones are the programmable logic devices, and of course you have something like sum of products. So sum of products means simply you've got the ANDs, which being the product, and then you've got the OR being the sum, right? So the same, if we take A, we've got the option of using either A as it is or the inverted version of A, because if you take any bit, you have one option of 0 or 1 being your input, right? So in this particular case, we've got A, where we can have, if this is 0, we can pick A as 0, or we can pick A as 1 on the output. Then we take that combination and then we can feed it into an AND gate, because if this is 1, then you can have the AND gate being activated, and the output, as long as this is 1, X, the output here will become 1, or it can actually be a 0 as well, depending on whatever combination we use. But the emphasis here is that we have created a programmable switch here. So we have various points that we can actually program, and later on we will see how the switch matrix also looks like. So we have the AND part that we can program, and the OR part that goes on the output. I'll just pause here a little bit to ensure that you can all hear me. Programmable ROM and how it led to the programmable logic device, and also we want to look at programmable array. So we are interested in adding an F here, right? The problem with these ones is that it was good, but we didn't have them in large quantities. But let's look at something. So the programmable arrays, you've got an A, and that can feed into a line, and this line, which simply means that if we want to pick an A, we can pick the value of A from any point as long as we set the switches right. So we've got a bunch of switches that can be programmed. Or if we want a not A at this particular point in time, at this particular input, we can pick not A from here as long as we get the switches programmed right. And the switch programming happens around this particular point in time. Same way, we've got it coming into an AND, which is like the sum of products, where we have A and B, or probably not C plus, so we just do programmable combinatorial logic there, or A prime and B prime, and then maybe the C, for example. And then we have the OR gates, similar to what we saw earlier where we saw the PLDs. So we can choose to have this sum of products there. But what you notice at this point also is that we can, of course, bypass the OR gate there. So we have the option of bypassing an OR gate using something like an exclusive OR. So if you want to look at the logic for an exclusive OR, you've got, again, let's use our X and Y as an input, where we have 0 1 0 1, and we have 0 0 1 1, where 0 0 exclusive OR means that only one input needs to be 1 for the output to be 1. So it needs to be exclusive. So here it's not exclusive, both inputs are 1, so it'll be a 0. Here is exclusive, you have one input being 1, and then we have another input being 1. So we can bypass and use other logics to get the output. And again, at the same time, we get some form of feedback from the output. So if it is a 1, we can pick, if it's a 0, we can pick the 0, a 1 here, or we can pick a 0 there. We get a chance to use feedback as well into the system. So we have several little blocks for these devices. At the moment, we are just looking at how the chips are created, right? And how the programming actually happens in terms of the physical device. So we have something called a macro cell in these programmable logic devices. So it's just like a basic unit. It's like a cell, the cell that makes up a human anatomy, right? Or you can think about it as like the basic atoms or the building blocks of it. So on here we would have had A, and we will have a line coming through like that with maybe an X there and then something like that. Right, so we've got our inputs, which we saw earlier, and then we've got the inverted version of the input, so we get both bits combinations. So each bit we get 2 possible output, which is 2 to the power 1, which is 2. Then we have the AND, so we have our switches going into an AND and eventually going into the OR gate as we planned. At least this is what we've seen so far. Now, if we want to see the working principle of a D flip-flop, which is a basic flip-flop, so it's got its input, which is D, and then we can synchronize it to a clock signal, and the clock simply move from just oscillate, continuous movement from 0 to 1, 0 to 1 onwards, yeah? And we can implement it and say maybe at the rising edge of the clock, we want something to happen. So for the D flip-flop, we can say at the rising edge of the clock, or when the clock is going from 0 to 1, we want this out, the value of the output to be equal to the value of the input. So if in a queue we have 1, 0, 1, when the first one comes in, it will stay there on the rising edge of the clock, the output will be 1. When the second one comes in, which is the 0, it will stay there, nothing will happen. On the next rising edge of the clock, the output will be 0. 1 comes again, it will stay there, nothing will happen on the output, but on the next rising edge of the clock, the output will become 1. So it just simply uses the clock to synchronize, and the output becomes equal to the input. So this part we understand. We've just basically found a way that we can have our input combinations based on the logic we want to program come in, and then we use the sum of products to get the output. But what do we do with the output for each individual of them? Remember, there are so many of them, maybe several of these. If we take that particular output, we have the option of storing the output as it is. So if this is a 1, on the next rising edge of the clock, or falling edge, depending on how it's implemented, we can store our 1 here. So the 1 basically gets stored. Okay, we also have the option of simply using it as it is without storage or without memory. So the 1 can just go directly there. And the multiplexer helps us to select. So we can set the value of multiplexer to 0 or 1 to use it to select what the output should be. So in this particular case, if the stored 1 is 1 or the next one is 0 and the value here is 0, we can use either 0 or 1 to select this, and that will set the output. Okay, so we have the option of storing that data or not, or just using it as it is, and then we can latch the output as well. So use sort of a controller to protect how the output is enabled. So this can be enabled to let the output out, which is a 1 as well. Or we can take that particular data and feed it back into the AND plane, or find the invert, so the 1 can come in, find the invert and feed it in. So in terms of an overview of what a macro cell is, we've got the input, we've got the AND logic and the OR logic there, so they help us to implement the PLD part. And then again, if we go a bit more into details, we've got the option of using a flip-flop. There are flip-flops in there, to store the data, or we can bypass it to use the data as it is, and we get a bit of control over the output as well. Then there is the complex programmable logic, or CPLDs, and we will be looking at the complex programmable logic architecture in a second. So it's got the PLDs. We started with PROM, then we use ROMs. Let's start with ROM there. Went to PROM. We did talk about RAM though as the volatile. Then we started talking about PLDs. That's a P. We've also talked about programmable gate arrays. And we have talked about the macro cell. So we want to look at complex programmable logic devices. So now we've just the same with the basic macro cell, but we have a larger layout of how the particular building block. So take this as a PLD block, take it as a macro cell or several PLDs laid out together, and it's similar to the way multi-core architecture works. So let's say if we draw our chip around it this way, of course the chip will be more external with the IO blocks feeding into these particular pins. So we have a chip that looks like that. I can't draw straight lines with pins, and then this can go out externally to them. Like that. But basically, if we take let me get rid of this, and we can use maybe something else. So we have the block for programmable logic device, and if we take the input-output logic, allow us to, of course, access external pins. And on the chip itself, we have an interconnect matrix. Basically, it's just a bus or a way that we can interconnect between these particular blocks, and they can link to each other. And of course, we have several of them laid out. That is why we call them complex PLDs, because they allow us to use various blocks. So you can actually, if you can implement maybe a flip-flop using this block. You can implement a little bit of other type of memory using this block. You can implement full adder maybe using 2 or 3 of these blocks, and all these blocks interlink together to form one big simple complex programmable logic device for us. So it's just an array or that is laid out of these smaller PLDs that we had. So we have the older, these are sort of the older versions of programmable logic devices. So if we look at simple similar one that is natural chip, which was the Max 7000, you've got the input clock, you've also got the output enable 1, output enable 2. We've got some pins coming into the internals of the programmable logic device, and we have the first macro cell A, and then B, and then we've got C, and so on and so forth. So you have one macro cell, and this one has this 1 to 16, and again for the first 1 to 16 input, and then of course continue to from 17 to 30 all the way to 64 in terms of the pins going in there. And we have already seen how a macro cell looks like, where you have the input, you take the inverted version of the input, you've got your AND arrays that you can program, and then you've got the OR that can take the output of the AND and then feed it into a flip-flop, or bypass the flip-flop using a multiplexer that takes the output of that particular flip-flop and the bypass as well, and you've got the option of feeding back in. So that's a few macro cells laid out connecting to input-output logic, and of course you've got your bus sitting on there for you. Altera is a company just recently been bought by Intel. They specialize in FPGAs. They and Xilinx own the majority of the FPGA community, FPGA hardwares, and they, of course, they are like the biggest players when it comes to FPGA, similar to the way that ARM is one of the biggest players for microcontrollers. But we have established FPGAs are not microcontrollers. You can use an FPGA to design a microcontroller, to implement a microcontroller, but not the vice versa. Okay. So then we look at Altera again. If we break it down in terms of the macro cell, how the macro cell looks like, we've got an input logic coming in, and then we also have the AND arrays going there, and we've got product term matrix, or we've got the OR matrix that you can actually say take the product in terms of combination of the ANDs, which is similar to what we saw earlier. We've got 36 signals in all coming in from the PA or PIA, and then you've got the parallel logic laid down. So again, we've got make some array combinations. We've got the OR, you've got the exclusive order you can use, got a bit of AND gate on there, which is basically the shared logic expanders. Then you can make use again of your flip-flop to enable the output or to set up the registers and feed onto the outside wall. The previous one we saw was much more simplified, of course, giving you an overview of how it looks like, and this is a real world scenario or real world case. So basically, our discussions from earlier have showed us how we can start off by creating a chip in the lab. Chips are expensive to manufacture, and it takes a lot of, it's a complex process, so it takes a lot of cycles before we get to manufacture chips, okay? But in this particular case, we are on the luck is on our side because we get to at least implement some things in the lab due to some things called PLDs that we started from, and we've seen that they can be complex, but the complex ones could only have about 10 to 20 or 30 logic cells. It wasn't really that big for us to implement larger circuits. So then came something called the field programmable gate arrays. They are programmable gate arrays, just as we've looked at, but they can be programmed in the field, meaning they can be programmed on the go, right? So you can basically just create them in the lab, right? And you have a large array of them, which means large layout of them, and we want to see how the architecture of the FPGA looks like. So similar to the logic cells that we complex logic devices that we saw, we've got some logic blocks. We've got loads of logic blocks, all layout, and these logic blocks have interconnect switches. The interconnect switches, we can program it to decide what logic block connects to what, right? So it's just a good large layout, and then we have the I/O logic, which will connect to the external pins, and even the connection to this I/O logic is also programmed using these logic block options that we have, or the interconnect switches. So the basic building block of the field programmable gate array, so basically they are programmable logic blocks, and that implements the combinatorial logic, and we saw the combinatorial logic like the sum of products that we saw earlier. Example, which is A and B and C, or not A and B and not C, and then we have an OR. So you have different combinatorial logics that can be created, right? And also it implements the sequential logic, because when we looked at the macro cell, we noticed that we have the option of using the flip-flops, right, to create sequential logic, which is making decisions in sequence, one after the other. Okay, then we also have the programmable interconnect. The programmable interconnect, some things like the wire to connect the input and output blocks, and also to connect the logic elements. But we should know that it's programmable. So we've got two programmable options so far. We've got the programmable logic, and then we have the programmable interconnect. And there is a third programmable block, which is the input and output. So basically, there are special logic blocks at the periphery or on the outside that can actually help us connect to the external world. You can have things like multiplexers and multipliers and all those things, or phase lock loops and other things on it. These are like specialized blocks that are also implemented to make life easy for us. So I love FPGAs just because they give us the flexibility to create large digital circuits on the go in the lab. So FPGAs make use of something called lookup table. Earlier we saw the macro cell, which is quite similar to what we will see for a lookup table, and that is what is used to implement the combinatorial logic. So they are not necessarily gates sitting at the bottom of it, even though flip-flops are made up of gates as well. But let's see what a lookup table looks like, right? So we can go into bit detail. So if you think about it, if you say, let's say if you have 0 1 1 0, the output should be a 1. So you got a table of reference there which have different combinations of A, B, C, and then D, or different input options. You've got 4 inputs lookup table there, and that would decide how the output should look like, for example. So we've got, it's like a reference or a dictionary where you see an input and then you take an output. So we've got the input combination will decide a 1 or 0 on the output here, depending on the references made in there. And again, we've got the option of latching that input to a D or a D flip-flop, or using a flip-flop. And of course, as we talked about earlier, rising edge or falling edge will do something. Okay, so we have it looking like that. And we will say we also have the option of bypassing it. So if it is a 1, we can store the 1, and if this changes to 0 and the input doesn't change, we still have the option of picking it, and we'll use a multiplexer to either select a 1 or 0 to fix the output, right? So we have our lookup table that it looks like this in terms of how the basic element works, and it uses a register for the sequential circuits, which is where we've got something like that. And of course you have additional logic which are not shown in here, things that you use like through the mathematical manipulations, like we saw earlier. I mentioned the multiplier for U, or you can have another, or you can have phase lock loop and other things, right? So this is a 4 input lookup table, and we've got the registers on there at the end as well. So let's have a look at how a lookup table looks like, right? So we have a lookup table of n inputs, and we want to use it to implement any combinatorial logic, which is the combination of both of them. So if we have 4 inputs in this particular case, which is 2 to the power 4 combinations that we can have, and we have, let's say, combinations starting from the least significant bit 0 1 0 1, so that's alternating all the time, and we've got the second one and all the way to the most significant bit alternating from 1 2 3 4 5 6 7 8, which is basically 16 in total, or combinations of them having 2 to the power 4 inputs. So we can say, okay, we've got a lookup table and of this, and whenever we have 0 0, the output should be 1. And of course it depends on the combinatorial logic that we are implementing to get these different outputs that we are taking on there. So that would definitely just feed into the LUT, where we have a black box that needs to be filled. so sitting on there, and we just say use it as a reference, and we don't even have to use the actual gate implementation. So we have the lookup table implementation, which is just the reference going into a black box, and then we have the output. Or we can have a gate implementation where we have the layout of the gates looking like that, but not a lookup table, just basically just with not a gate implementation, but it is a lookup table implementation for the FPGAs. So let's look at how the programmable interconnects look like, right? So we've got the logic elements made up of lookup tables that's sitting on there, and we can have various hierarchies which are not shown here, but we are saying that we want to find a way of creating very fast interconnects, right? So we have the horizontal, vertical lines of various lengths that we can create, or we can program them for them to work. So we have a logic element, another logic element, another logic element. This may implement another or something, or different type of implementation of the circuit. But then we can say we set a switch here that creates a connection between this logic element and the output. Again, when we reach here, we can set a switch there, so internally connect them, and we can use it to also connect it. So it's just programming of the way that we saw, same way that we saw the programmable logic devices connected in that array. So just use that to create various switch connections to connect to the output on there. So good, with these programmable switches we can connect or route various components onto the other side. So just say routing, but basically just connections that are being created for us. Yeah. So let's look at how the switch actually looks like. So we talked about VHDL, which we'll go into details, and we say VHDL allow us to sort of create circuits in the lab, which is basically allow us to program these field programmable gate arrays. And we've gone all the way from ROMs to CPLDs or PLDs, and eventually ended up on FPGAs. And we have the gate arrays. We looked at macro cell before. We've looked at lookup table, and we say lookup table is not necessarily gates, and we want to look into how these switches are programmed. So we've got a switch box, we've got a matrix, and we've got various options that we can, of course, tap from, and the gist boxes are just sitting there doing nothing, like there's no connection to them. Now let's look at how we can create these programmable connections. So like we've got one, maybe the west going all the way to the north, we've got the east going all the way down, so we're going to start with the west, and then we've got connection on there. So let's see how these connections are being made, like the connections on there, how the switch box works. So we've got a layout where we can have one wire coming in, wire number 2, wire number 3, wire number 4. At this point, none of these are connected, just a layout of switches that forms the break. So if we want to connect 3 and 2, we just close this switch, and then this new connection will be created for us. However, let's say if we want to connect maybe 4 and 3, we just close this switch, and this will be connected for us. Or we say we want 4 and 2, we close that switch, and we have a line created for us here. Same way, 3 and 1, close that. Or we want 1 and maybe 4, close this. Or we want 1 and 2, we can connect the link on that side. So it's just the state of these particular switches that determines what input or what part of the FPGA is routed to what. So because these switches are programmable and we can switch them on and off, we get different things. So there are 1, 2, 3, 4, 5, 6 of them. So we have 6 pass transistors per switch. interesting. Per switch matrix to interconnect a point, and the pass transistors, these transistors will act as programmable switches, of course. And also they are driven by the configurable memory, so you just write your code to sit in a memory, and then it can just help you route these lines. So that takes us to the end of the main presentation, which talks about the background of FPGAs, where they've come from, how they've evolved, and how the FPGA architecture looks like, how it's implemented. And these FPGAs are the chips that allow us to run this logic that we'll create with VHDL, and it can help us program the chips and run them in our labs, or probably for me to demonstrate to you what I'll be doing from my side. So I'll stop the recording.